Hello, y'all. Barely Berry Jr. back as promised. Uh, we'll be doing some girls. So I actually uploaded my file, but for some reason I can't find which folder I put it in. Let me see here. Not sure why it's not showing on the list like it should be. Oh, I see. There's some kind of error going on. So we'll be doing some Gaussian integrals. And as you all can see, I'm wearing the shirt of my new school. Usually I'm wearing UT stuff. But I'll be starting to wear some SMU stuff since that's where I'll be going. So on my other channel, I gave a sort of rundown of what I'll be studying and things like that. So, but I can talk about it a bit here as well. If somebody have any questions, I'll probably saw my, at least a few, some my previous upload where I uploaded my graduation video. So that was cool, fun to upload. And what I've been doing is, so in graduate school, one of the things I have to do is cover all of the foundational stuff I did in detail. Classical mechanics, quantum, thermo, and thermo, what's the other one? Classical, quantum, thermo, and EM. So the idea is that we have to understand these things to a very high degree before moving on to actually doing PhD research. So one of the classes that we have to take is a foundations course where we basically review basically all of undergraduate physics in one semester. So the idea is that we have to do an exam every week and cover all of the basic material. So what I plan to do is to help prepare is to, sort of review everything that's going on with that. And one of the things I need to do is go through the textbook again. So I find that that's a very convenient thing to do as far as learning. So going through the textbook, what I found was that when I got to reading the quantum textbook again, and those of you who have been following along, I could share the cover perhaps. Well, I'll share the cover momentarily. For those of you who have been following along, uh, and that's what's going on. Those of you who've been following along, you remember the quantum book is the what do you call it? Uh, Griffiths. And so what I plan on doing is I'll just go ahead and read through the book. And as I get to something that stumps me, I'll go ahead and cover that. So the first thing that I really hit that I had a problem with again was Gaussian integrals. So I'll talk a bit about Gaussian integrals and we'll review a bit about how that goes. And we can go with what I've learned or relearned about solving them, since apparently they're such a very key component of things like uh, such. So I'll share my screen momentarily and we'll get into that. That's shared. Boom. have my new window ready. So here we go. Y'all can let me know if you have any questions about anything, as usual. And there we go. And I guess I shall go ahead and keep it, put the horizontal one on. Boom. All right, that's better. So the idea is, and I'll put them Gaussian integrals. So the idea is that when you're dealing with quantum particles, and remember this is dealing with quantum mechanics. So you notice I made the title of this one a bit different because, oh, I need to change my title. I made the title of this a bit different because I'm not necessarily going to be reading the textbook. I think I read a lot of this part already, as far as the earlier parts of the textbook. But if y'all would like to see me go through the textbook again, perhaps in more detail, let me know. I figured since I sort of read these parts of the books with y'all before, I'll just go through some of the more difficult concepts. So I'll just put Gaussian integrals. So the idea is that when you're dealing with a quantum particle, it has a distribution of its probable position. So this is going to be, let's say, the x-axis, and it would look something like this. And the idea is that this is the sort of the integral of that, something like this, as far as the probability density. And basically this sort of graph, like this would pretty much be the mean right here in the middle. And you have something in relation to this called the standard deviation. So the standard deviation is basically how far away you are from the mean. So if I were to, hey, what's going on, Catherine? Yes, I like it as well. So I have like a few of them. So I'll be swapping them up from time to time. And if you look at this, it's quite interesting because, like, let's say if I put a positive value for this number, for x, then it's going to be e a positive number squared. And the farther I go to the right, this is going to be in the denominator. And that's how it goes down like this on the right side. And by the same token, if I'm on the left and there's a negative in front, but this negative number, whatever it is going to be squared. Still equals e to the negative x squared on the left side. So even though the shift is initially to the left, it still gives that decline in that way. So that's how it ends up being a mirror image of the other side. So this is basically the distribution that a Gaussian will give us. And now the most difficult thing about this, and I guess it's fair to point out what the problem is, the problem that the book brought up that made me want to get into this in more detail. And by the way, I noticed my pad is not showing properly on the left side. Let me adjust that a bit. Okay, so y'all should be seeing the, what you call them, scale over a bit. And that should be good, I would say. Close enough. All right. So this is the problem that the book brought up. It said I have a probability density of this, and it basically wants us to find the value of a in this integral, and then uh, find a bunch of other things like the expectation value of x, the expectation value of x squared, and the standard deviation, which would be um, if you have basically a distribution of values, the standard deviation tells you how far these things stray from the mean. So in other words, if I have a whole bunch of values and this is the average value here, this doesn't go too far away. But if I have something that looks like this, then the standard deviation would be a whole lot bigger. So it sort of like gives you a relationship between the average value and the rest of the values and what we're talking about. The difficulty I had was, so if you want to get, you have a probability density and you want to find out what A is, the trick that they use in quantum mechanics is like if you, like you're dealing with particles. So if you have a particle and it actually exists, is going to be somewhere. So the probability that the particle is going to be somewhere is 100%. So this probability density basically lets us know, like if I integrate it over all, space, it'll end up being 1 or 100% probability that I'll find the particle somewhere. So the idea is that since we know this is going to be 1, if I have an unknown value up in here somewhere, I put all the values in for x, we can just consider x and a to be just constants. So we don't necessarily know what they are, but we have to know what a is, like the capital A, because it's basically the normalization factor that allows us to properly get percentages. So let's say we might know initially that the distribution looks something like this, but we don't know what the values have to be. So it ends up calculating to 1 when you take the full integral. So you might have to scale all of these values to something so that when you do take the integral, it does equal to 1, and then you're dealing with 100% probability, which would be the case, if something is in reality. So to work on the basic integral, it looks something like this. And there's a trick to calculating this thing, which is quite interesting. So if I wanted to take this integral, like apparently one of the things I noticed is working this out, if you were to do this integral like this, for one, it'll work out crazily because you'll end up with 0 minus infinity. So basically you'd be putting in infinity on one side for x and negative infinity on the other side. So one of the things they often do is multiply it by 2. So I'll say like, let's say I prime equals, um, or I guess just to say I equals 2 I prime, which is 2 times the integral from 0 to infinity. Because the idea to keep in mind is that this distribution it's equal on either side is the mirror of each other. So the area under this entire thing is basically 2 times the area under any one half of the curve. So because of that symmetry, we can just go ahead and take half of the positive side and not worry about the negative side that'll give us infinity on that side, and it makes the calculation easier. Another thing that makes this more difficult as well is this integral is apparently it's just hard to do. I guess there's not necessarily a numerical way to do it directly. So what they do is they take I squared instead, and I'll just do it with just the regular I and say we have negative infinity to infinity of e to the negative a x squared dx. And for some reason, there's a mathematical thing we can do. We can multiply it by the same thing, but call it y squared. So basically multiplying these things together, we know that the integral is the same integral. So whether I call this axis here x or I call this axis y, the area under the curve will be the same. So when I square these things, even though x and y is different, I guess because since they'll give us the same value no matter what we call the variable, I could just call this I squared because both of them equal to I. So I guess that would be the reasoning of how you can do that. And then we go through this nonsense here. So I'll combine these. Right? And then we can go ahead and utilize the rules of exponents and combine these again. So all I did was just sum these exponents together, extract the negative and put it on the outside. And now I have a, in one sense, a more complicated integral because now it's two different variables multiplied together, but this allows me to recognize something about this. And let me know, Catherine, anybody else who's watching, if you have any questions or comments. When I tried to download this file again, it was having some kind of error. So I'm going off memory at the moment, but there we go. No more error. But I would like to make sure I could check my notes to make sure I don't make a typo or something. So it looks like whatever error was going on has corrected itself. So all good. What do y'all think? Questions, comments? Guess everybody's good. It looks like I uploaded the wrong notes. That's not going to help, but I think I know it well enough for all to keep going. So the idea is that, and this is what I found quite interesting looking this up. So x squared plus y squared and polar coordinates is r squared if we make x equals r cosine theta and y equals r sine theta. So you all might remember that from, I think this is a pretty common correlation right there. And what we have to do is basically convert this into polar coordinates. And then we can use the fact that this is equivalent to r squared to simplify this integral. And then we'll have a simple integral to solve, apparently. So if we look at this in coordinate form, what we had before was this is x, this is y, and we want to have an area under the curve. And this will be basically dx, this will be dy, a little bit of a distance in both directions. So area is going to be dx dy. And Catherine says these calculations look complicated, but they're actually as easy as hi. Yeah. I think the hardest part for me is just remembering these tricks. I guess I like integrals, but I guess I'm used to doing just regular integrals. I mean, I like integrals and derivatives, but I guess the farther we go into physics and math, the more integrals you have to do that you can't really do. So you have to find all kind of tricks to doing them. But if you just do this the regular way, it just doesn't work out. So you gotta convert it. Now we was to look at this. Um, in one way, this is a bit more complicated because the area looks like this now. And I'll clarify what this is momentarily. But I also call this R. I also call this theta. This distance here is R theta or R d theta. And this here is dr. So it's like how I can take the area of this little box now to make that the area that we're looking for. I can see that the area is R dr d theta. There's actually one convenient way to actually convert this into polar coordinates. So I can actually take this integral down here and I can say it is integral e negative a r squared r dr d theta. So that's one way to do this. Uh, oops, and I apologize. That's going to be so basically this infinity is sort of like a filler to mean over all space that you can possibly do. So if I'm going to look at r over r spaces from 0 to infinity, because I'm looking at this, uh, this would be the origin here. So technically this would be, you know, r plus something to r plus something else, but you get the idea. As far as this being the origin, I can go in a direction out from this point, but I can't like, if I go to the other side, it's just jiggle the radius out from that point. So that's just r to infinity, be 0 to infinity. And we know that this can go around up to 2 pi. So theta goes from 0 to 2 pi. So that's our integral there. And just remember that this is still I squared. So therefore, we don't even need to uh, do this, even though I saw one way where they sort of did this and did something else, like they cut that in half. But doing it this way, it sort of cuts it in half automatically. And the answer should end up being, if I remember properly, square root of pi over a. So even though I'm not looking at my notes, let me see if I can get the same answer, knowing that's what it should be. So if we look at this, there's no variable for theta up in here. So I could just plop a 2 pi up in there. That won't be a problem. We have this, and the 2 pi is basically the integral of the theta. And this part, since I did this transformation, I could actually just do this integral as normal. So we still have 2 pi in the front. We have, this is going to be the same thing again. If you have an exponential, you always write it over again. Then you need to take the derivative of this and divide by that. So this will be negative 2RA. And I have to remember this R is still there. And what happens is a few of these things cancel. So I have R canceling. I have the 2's canceling. So I end up with pi over A e negative a r squared from 0 to infinity. And now all I have to do is just plug in. So I have pi over a, and we multiply by everything. So then we have e to the negative infinity, because basically I'm going to plug in an infinity for r, and infinity squared is just infinity. And a, whatever that value is, like we said, it's some kind of number, it's still going to be infinity. And there's going to be a negative there. So really this is going to be 1 over infinity, because it's 1 over e to the infinity, basically. And I have to subtract. I left my negative off here. So I'm subtracting a negative. So I add that. And again, this pi over a is already in the front, so I don't have to worry about writing that again. So now I have 1 over e to the 0, because it's negative, but I mean, it doesn't really matter because it's 0 is going to be 0 either way. So now I have pi over a times, and let me know if you have any questions about this, how this is going to be 0, because it's something divided by infinity. And this is going to be 1. So 0 plus 1 is just going to be 1. So this ends up being pi over a. And we said this is equal to I squared. So remember, I multiplied it by another integral of the same value but with a different variable to simplify it. So that means that I equals square root of pi over a, which is what I knew the answer should be. So this is basically the idea of working out these Gaussian integrals, which again are integrals that always give you some form like this, a sort of bell shape, where we can basically get the value of the spread of the variables away from this central point, this most likely point. And now going back to the original integral, you can basically integrate from a problem. You could basically do everything we did to integrate any integral that looks like this. And if we were to examine how they correlate with each other, and I'll delete some of these lines. So let us stop here. So actually, yeah, let me just copy the whole thing down. I'll just copy this down so we can compare. So if we look at this, the integral is basically the same. Like if I were to call this lambda a instead, I mean, all that means is just that this will be a lambda here instead of an a. So we know that whatever is multiplied by that goes into the denominator. And I can actually take this x minus a and just call it u with a u substitution. And it ends up working the same exact way. So this is actually how you solve this integral here, even though it seems a bit more complicated with the um, the little shift on the x there. But the distribution will end up being the same. In other words, if I were to shift this entire distribution to the left a little bit, I mean, it's still the same distribution. It's just the variables on the values of the x-axis will be a little bit different. So what that means is that if I were to actually complete this whole integral out, and we know the integral equals this, I'll end up with a square root of pi over a equals 1. So basically, the integral of AE, and it's just some variable we don't, like some number we don't know what it is, negative AU squared du equals, we know what its integral is, we did it earlier, so I'm just going to multiply by that equals 1. So A equals square root of A over pi. That's what that variable has to be to cause this whole thing to be equal to 1. So there you go. So slightly ugly business as far as doing the integral. It's not too crazy. Um, but I didn't want to go past that part of the book, not having a um, better understanding of it. So this part of the book, by the way, is chapter 1, section 3 of Griffiths. Perhaps I can share that really fast. Perhaps what I'll do is do a little bit of reading while I'm here. I went a bit, it didn't take too long, took less than an hour. I like to go for about an hour. And why don't this window in here and capture this, and there we go. So that was the problem I was pointing you all to right there. And I'll take a look at the next section while we're here. Take up the next few minutes that we have, and y'all can let me know if y'all have any questions about the integral that we did. Boom. So the plan, by the way, is to get through the book over the summer. I'm actually taking a class for fun, which I'm vacillating on taking or not, but actually would like to keep a class going. And I've been meaning to read some Greek literature. So it's like a class on Greek mythology. So I think I'll still take it. We'll see how it goes. Um, but suffice it to say that I still plan on reading this book over the summer and perhaps in my classical dynamics book. I know somebody wanted me to do chapter 2 again, chapter 2 or chapter 3. I have the video up, so I'll likely be going over that over the summer as well as I review those sections. So, by the way, if y'all are curious about what this means right here, so I actually did the derivation before, not a long derivation, but uh, like if you wanted to get the standard deviation or something, it's basically the square root of the expectation of the squared value minus the expectation value squared. And the expectation of the squared value is basically you're adding up the value squared and the probability of the value. And the one with the not squared is similar. And it's important to note that this squared does not equal, normally, it does not equal uh, this squared. So else it always equals 0. So when we look at this, we all do section 1.3. This is one of the textbooks that I actually enjoy, by the way. I think Griffiths did a pretty good job. I'll show you all the cover really fast in case you don't recall. So, interestingly enough, even though I never read in detail about Schrodinger's cat, apparently it's about whether like the cat inside the box is alive and dead at the same time or something, whatever. Um, by the way, I took a look at the when I was doing the stream on my other channel with when I talked about the classes I'll be taking at SMU, I actually uh looked over some of the details of the classes. I noticed that the topics that are covered in that class covers topics from this entire book. Like in Quantum 1, we basically did this first part, and in Quantum 2 in undergraduate, that's when we moved to perturbation theory, where you basically have a particle in a box, which can be a particle which we found near a proton or something like that, like an electron near a proton, and you perturb the well a little bit, like you do something to make the energy change at one point, and then you find out what's going on with the particle there. I noticed that the class covers all of that in one semester, so sometimes going to be a pretty hard class. So not only are we is quantum our weakest subject, but then we'll be doing more of it in one semester. So that's why I'm going to focus on studying quantum. Tutoring says I attempted to read that book at university during my breaks, and the university library brings back horrible memories. Really? You talking about the third edition? Never actually saw the earlier editions. I don't know how long this edition has been out. Maybe I could look it up really fast. This one came out in 2017, 2017, 2018. You know, I don't know if you're looking at one of the earlier books. And I guess I'm comparing it to other books I've read. I mean, at least it doesn't seem like he is like trying to, like I told my thermo professor, we were talking one time about me and another student that was in his office hours talking about the textbooks we like or don't like. And one of the things I said about this book and our thermo book, by the way, is that they're written in such a way where it doesn't seem like they're trying to be like, oh my gosh, look at how well I know this topic and how sophisticated I can write about it. It's like they're actually writing for us to learn, you know? So that's the one thing I like about this book. It seems like perhaps more map books I've read, it seemed like one of the death knells of what they say is that's trivial. Like talk about some kind of derivation. And then they're like, oh, that's a trivial, that's trivial. We're not going to worry about that. You know, it's like, what the hell? Let me turn this way. And, oh, that's why this thing was mixed up. Ah, a Schrodinger's cat one. Interestingly enough, I don't remember us talking about Schrodinger's cat a lot in the class. Uh, I don't know what's up with that, but I'm gonna have a general idea what they're talking about. Let me make this. Mm, turn this sideways. Let me just scroll this up a bit. Interesting stuff. I worked last night. Yeah, last night. No, I don't know what night I worked. There's no reason why I'm at the schedule is off. Sorry about earlier. I probably shouldn't have scheduled that for Sunday because my apparently if I work two night shifts, I'm all thrown off. So maybe I'll make this, even though I don't know what my schedule is going to look like in the future, but I'll probably make one on Saturday, which I'm used to Saturday, whether I work or not, and then one on Monday. It seems like that'll be easier for me to keep up with. So that'll likely be the plan. Saturday on my general channel and Monday on my STEM channel. And we'll see if maybe I'll add another day somewhere. And if y'all like uh, um, Greek mythology, I can even make something about that as well. All right, so let's look at, hold up, look at normalization. I just had from a 1.4. Oh crap, 1.4 normalization. So let's read this section really fast. See what it's talking about. Now return to the statistical interpretation of the wave function, right? We're just reiterating that the integral, which is what I said up here. So this is the probability density function. It's like the way of quantifying the probability of finding a particle at a certain spot. And probability density function. So that's why earlier I had the integral of this, negative infinity to infinity dx. And when you look into quantum proper, they have it like this on the in the book, which is the infamous psi. What was I reading? I was reading something. What was it? I was reading something that put us on to. Oh, you know what? I was reading this book, thinking about earlier in this book. It talks about how it was talking about the origins of this equation, the Schrodinger equation in psi. And since I'm going through it for graduate school, I've been going into more detail as you see with me stopping for the um, uh, Gaussian equation. But one thing they mentioned in this book, I'll see if I can find it really fast. It talked about the how the how the equation came about, and I actually looked up the paper. It's a pretty good paper, actually. Maybe I can go over it one time. It was basically the guy who was the student of one of these people who discovered this stuff. He actually just wrote about the sort of background of how they discovered the equations and what was going on at the time. Um, I don't remember actually where they mentioned it at, but yeah, it's not a big deal. So we have that, and this requirement should disturb you. Determine. All right, so normalizing the function. Now they're talking about proofs. All right, so maybe we should stop here and do this proof. When I say stop here, I mean let's actually read this part. So it's talking about how this equals 1. However, this requirement should disturb you. After all, the wave function is supposed to be determined by the Schrodinger equation. We can't go imposing an extraneous condition on psi without checking that the two are consistent. But at a glance, at equation 1.1, and we'll review that momentarily. So 1.1, they mean by the actual Schrodinger equation, IH bar, first derivative of psi with respect to d, is negative h bar squared over 2m, second derivative of psi with square root to x, plus v psi. It reveals that if psi is a solution, so too is a psi of t, where a is any complex constant. What we must do then is pick this undetermined multiplicative factor so as to ensure that equation 1.20 is satisfied. Now, interestingly enough, they gave us this problem on normalization already. Uh, unless I jumped the gun because I knew it was supposed to be equal to 1. Maybe they didn't want us to make it equal to 1. But technically, this was normalization, what we just did. Let's see what they're saying here. The process is called normalizing the wave function. For some solutions to the Schrodinger equation, integral is infinite. In that case, no multiplicative factor is going to make it 1. The same goes for the trivial solution psi equals 0. Such non-normalizable solutions cannot represent particles and must be rejected. Physically realizable states correspond to this square integrable solution, Schrodinger's equation. Catherine says, I would find it easier if I could read along, but it's too small on screen. Can you make it bigger? Yes, I can. Why don't I, we do this? So I'll move the chat here. And I'll move the heft up. Here. And that would allow me to spread this out a bit. and resize it. There we go. So that might help, and perhaps making the text actually bigger on the screen might help. Okay, maybe too big. Okay, what about that? That seems readable enough. What do you think? I'll just cover y'all know I offer tutoring. From with my AP Physics student over the last semester, so I'm free again for more tutoring students if anybody's interested. And perhaps I'll move the chat out the way a little bit. All right, some good. Thanks. All right, so square integral. So it says square integral, square integrable. Not sure what that means. Maybe the dictionary will tell me. Oh, let's look this up really fast. Square integral. A square integrable function is a type of mathematical function whose squared absolute value has a finite integral, meaning it can be calculated over a specified integral. Well, that makes sense. So they're just saying that when we square this, going back to the book, which is must be part of the reason why it's psi squared. When we square it, it actually gives us a definite value. So that makes sense. But wait a minute, suppose I have normalized a wave function at a time t equals 0. How do I know that it will stay normalized as time goes on and psi evolves? So in other words, if I get a value for an equation for psi, and I do this thing that I did here to solve for what a needs to be to make this equal to 1. So now I know that we have a 100% probability of finding a particle somewhere. But if I do this at c equals 0, like, if I call this moment 0 and I know I have this probability of finding a particle somewhere at 100%, how do I know 10 minutes from now I still have a 100% probability of finding it somewhere? You can't keep renormalizing the wave function, for then a becomes a function of t and you no longer have a solution to the Schrodinger equation. Fortunately, the Schrodinger equation has the remarkable property that it automatically preserves the normalization of the wave function. All right. I don't know if Schrodinger intended this when he found the equation or if it just happens to be a function of the equation. I believe I remember right, his paper was something like linear algebra as solutions to quantum, something like that. I could pull up the actual article and show it to y'all. So I'll let that load while I'm finishing this. This is important, so we better pause for a careful proof to begin. So this is interesting. So we have our function, and now we're going to take the derivative over time of the function. And now they're simply bringing the integral in. So basically what we're trying to say is we're changing time, and now we're seeing how this thing evolves over time, which is why we're taking the time derivative of it. It's interesting to consider that derivatives is really like, at least if you take a derivative over time, it's like you're changing time. You're moving along in time and seeing what changes in the function. But that the integral is a function only of t. So I use total derivative d over dt on the left, but the integrand is a function of psi as well as of x as well as t, because a partial derivative on the right. So I missed that. So in other words, if I take a derivative of the whole thing. I can do that with respect to this t alone, but since psi is a function of x and t, as we can see in the middle, I have to do partial by the product rule. Is interesting. So one thing to keep in mind about this is when you have psi x of t, there's going to be some equation that solves the Schrodinger equation. And when I do this, it's also called mod squared. What that really means is we're taking the complex conjugate times psi, because we found that in quantum mechanics, uh, it works with complex numbers. And complex numbers are numbers that include I, which is the square root of -1. So, for instance, if I have the complex number 5 plus 6i, for instance, if I wanted the magnitude of this number, then I would have to do 5 minus 6i, which is the complex conjugate, times 5 plus 6i. And what this does is this plus minus thing actually helps get rid of the complex number, so we actually get a real um, um, you know, magnitude. So if I was to show you what this looks like, it'll be 25 minus or plus 30i minus 30i plus, this is why I say plus, by the way. I mean, that's minus 36, but I is the square root of -1, so now this is times a -1. So this becomes 25 plus 36, and that's what, 61? So therefore we get a real magnitude even though you have a complex number. So that's why this is done this way. That's why the book is writing it that way. It's because psi squared is actually, when you square it to get a magnitude, you actually have to take the complex conjugate, which means every single um, complex number, we change the sign in front of the complex number. So, and this is a brief aside right here. So, we're going to multiply this out. I'll try to multiply it out inside of the brackets, and I'll finish this proof here, and then we'll call it a day for today. So this should be, just write it out. So using the product rule, I have psi t, psi plus, which is what they did there. So I wrote mine in the reverse of how they wrote it, but that's what that is in the middle. And the Schrodinger equation says that psi of t is that, and psi prime of t is that. So I imagine we're going to plug that into the equation, which gets very ugly. And by the way, looking at the equation, all they did was just solve for psi of t. So if you look at this equation 1.1 and you solve for psi with a partial derivative t, all you have to do is just bring the I over h to the other side, and then it becomes 1 over I over h bar multiplied by the whole thing. So then if we look at the equation here, we see that it's just that is multiplied by 1 over I h bar. So that's all they did, was just solve for 1 over I h bar in the Schrodinger equation. So let's go ahead and plug this in and see what we get. We end up with negative infinity, infinity. um, negative I h bar over 2m partial squared psi over partial t uh, partial x squared, so replacing the psi of t, plus I over h bar v psi plus, oh, and times psi. This is going to be all plus psi star I h bar over 2m squared psi over x squared minus I over h bar v psi dx. And if you notice, by the way, there's a negative here and not here because it just changed the sign of the complex conjugate. So if you look at this very closely, you see that this is positive I, negative I, and here is negative positive because it put a negative on the complex conjugate one with the asterisk for the reason that I showed you all here. So there's put a negative wherever you see the I, and then you get the flopping of the signs. So now we get this. So the partial derivative of psi squared looks like they factored out the I h bar over 2m. And did I not multiply an I h bar over 2m in here? Oh, I see. So it looks like this cancels. What I'm noticing is we have a v psi star here minus a v regular psi. The v goes away here. Only thing I can figure is that oh, that's what it is. So this thing skips some steps, but it doesn't skip a lot, but I guess it skips enough. But this is what they're doing. If I multiply this in, I'm going to have negative I h bar over 2m squared psi star over x squared times psi plus I over h bar v psi star psi plus, did I leave off a, I'll put it on the front, really, plus uh, I h bar over 2m squared psi over x squared. And again, all I'm doing is just distributing the psi that's multiplied in the psi star. So this is going to be psi star here minus I over h bar v psi star psi. So as you can see, these things are the same, and that's why they disappear. So they just skipped a step there. So almost to the end of this thing. So now we're able to do what they did there and factor this out. So I'll factor out I h bar over 2m. Now I have second squared psi over squared psi star minus second squared psi star over x squared psi. And let's see what else they do. So I vaguely remember a professor, oh, I see. literally all they did was factor out one of the side squares here. I'm just going to just copy this down. I mean, one of the sides out of the side square. So if I factor out one of this one, this becomes just 1. And I just put this on the outside. So it looks like we're still on the same page. And apparently this integral can be evaluated directly. So, because we have this by dx, and since this is a partial derivative of x of something that's being integrated by x, the integral just goes away. So ironically, it just ends up being what it is. Tricky math stuff. All right, so we have that. Still evaluated over infinity and negative infinity. And it says, but psi must go to 0 as s goes to infinity. Otherwise, the wave function will not be normalizable. So they're simply pointing out the fact that um, as x gets bigger and bigger, since I'm going to negative and positive infinity, again, looking back at the general idea of the distribution, that even though from negative infinity to positive infinity is a probability of finding something in here, but we can see that the farther away from the mean we get, the smaller the value gets to eventually it hits 0. So you can actually have a value of 1. So if this stays above 0 for all eternity, then the area will be infinite. So it has to go to 0 at some point. So what they're saying is, since this goes to 0, when I plug in infinity for this, it's going to equal 0. So this equals 0. So the integral is constant with respect to time, and thus is normalizable. So this is basically the proof that even though we might look at this particle at a later time, the integral as a function of time over all space ends up being 0. So the normalizability doesn't change. So that's that. So a little bit over. Hopefully you all enjoyed. And I think I'll look for the schedule that I had mentioned before, where Saturday will be the STEM, and I'll see about making Saturday the other channel and Monday the STEM. If y'all have a particular day, let me know. Because at the moment, my schedule, at least for the summer, my schedule will be pretty open as far as when I do things, as long as I'm not working. And uh, for the rest of this month, I'm working every weekend and one day in the week that I picked. So they're making a schedule for June, so I'll see how that goes. So if y'all want a different day than Monday for STEM, let me know. And Catherine says, Carol, the math is easier than wrapping my head around the concept. Yeah, I get that. That's part of the reason why I did so horrible on the second quantum exam. And I mean, I got a 58 on the final, but again, I did so well in the earlier parts that I was able to get a B out the class. But apparently, a lot of people did bad on that final because he had to curve the grade. He told us in an announcement sort of thing. And it was mostly concepts. So, yeah, well, maybe I got to get better with that. But awesome. Always good seeing you, Catherine. Good seeing, I know a lot of people popped in. Make sure to drop a line sometime. And y'all can check me out on my other channel on Saturday. And I'll be back here, if not Monday, probably sometime during the week. I'll schedule a Monday and work on getting a day that I can comfortably meet every week, a day and time. So we'll shoot for Monday and perhaps a bit later. By the way, Catherine, what time is good for you on Monday? Is this time good, or would 8 o'clock be better, like the regular time? believe it must be, what, 8 o'clock by you by now? 8 p.m., I think. Thanks for the links. Anybody else has a time preference? Awesome. Sounds good. I'll look for you on Monday. I'll try to keep an eye on keeping it earlier since I know yours is later. But pretty much any time will do. I'll keep in mind that the regular 8 is good as well. Thanks for posting the link, Catherine. Be sure to sign up to the Patreon. And I'll see y'all Saturday on my other channel, if not earlier in the week on this or the other channel. Y'all have a good one.